Hello guys, so in this video I'll be describing the solution that I finally submitted in this competition, which is CSIRO Image2Biomass Prediction. So I guess I have created a post for it, so where I have like described like how I got this 149th rank in this competition. So this video will be regarding like what all strategies I did, so what models I trained, and how I land up in this 149th rank, and I got my first silver medal in this competition. Cool. So let's get started with it. So this was a you can say image regression problem. I'll just bring this guy here. Okay. So this was a image regression problem. Okay. Because here the input was an image. Okay, just like not like this. Okay, I can show you the data. Yeah, so the basic premise of this competition was, so they have given us some crop filled images, okay, in a top view manner, and from that we have to predict biomasses. Let me expand this. Okay, so there were 5 categories of biomass that we have to predict. So I will just list them down. So the first one was greenness. Okay, how much like grass or like how much green stuff it has. Okay, the second one was clover. Okay, so for clover I will show you like what exactly is clover. So clover, you can think of like if you guys have played um, what you will say cards game. Okay, so clovers are basically like leaves, something like this. Okay, so these kinds of leaves are very nitrogenous, okay, to the like to cows and other cattle. So they wanted us to predict like how much cloverness it has. Okay, the third one is dead. So in this picture you can see the dried out stems. Okay, this yellow stems. Okay, those are like dead particles, because if any cattle eat them, so not much health benefits they will get. Okay, so they wanted us to predict this. Okay, then the fourth one was GDM. Okay, so this was basically a summation of how much greenness and clover it has. Okay, and the fourth one, the last one was total, which is summation of our GDM plus dead. Okay, so it's total, you can think like this is the basically summation of green, clover and dead. Okay, so yeah, there were 5 categories of biomasses we have to predict, and the input was an image. So you can see like the data set size was 1.11 GB, so it was a little bit large data set. Okay, cool. Now for the evaluation thing, so they set this metric, which is a weighted R2 score. Okay, and you can see here they have given a higher weightage to GDM, which is this some like GDM and total. Okay, total being like zero 0.5. Okay, like the highest weighted, and the second one being GDM, which is 0.2, and rest of them were 0.1 categories. Okay, cool. So in this competition, the most difficult task, I guess, for all of the competitors was how to predict clover and dead properly. The reason being, if I show you the EDA of them, okay, I guess this is the EDA. Yep. Do I have any proper diagram? I guess not. Okay, let's stick to this. Okay, so in this competition, the dead and clover quantities are very you can say negligible in an image. Okay, couple of images had only clovers where your greenness has to be minimized. Okay, but for majority of the images, okay, you can see the clover values are pretty low. Okay, so that was a major deal. Okay, but whereas if you see greenness, they have a good curve. Okay, the values are mostly above like 5, you can think. Okay, and but if you see in the case of Clover, okay, those values are pretty low. And similarly for Dead also, this was the same case, okay, same as Clover. And the difficulty part for Dead was, so suppose you have a top down view, right? Let's change the color. Okay, so you have a top down view, so you have a dead particle here, okay, a dead stem here. What was happening was, in the image, let me choose a different color. In the image, these dead particles were covered by some leafy particles, okay. So the way they have curated the data set, like they have done their image photography and all that, and they have their own set of tools to predict how the like how much deadness this image has, okay. But when you are giving us the photo of this top down view, okay, this particle is completely hidden. You can only see this small portions here, okay. From this we have to predict how much deadness is there, okay. So this was a major challenge in the competition, okay. So yeah, the major challenges were to predict Clover and Dead, okay. For, I guess, majority of the model in this competition would have like successfully predicted greenness, GDM and total, okay. And what could have been happening was, so your greenness might be overruling Clover and Dead, okay. Basically majority like the green prediction would be dominating your GDM and total calculation. So yeah, so this was a challenge. So what I did, okay, so in the data set, they have given us some metadata fields, okay. Those are like sample ID, image path, like the path to the image, sampling date, okay, so the date on which they collected that image. uh, so most of them were happening on the same year. They were only varying between the months, okay. Then across what all region they have collected these images, okay, what kind of species they have collected. Then there is some vegetation index that they have given, but let me tell you, this guy was not at helping, okay. Then also they have given height, okay. So the competition host has claimed that you can use this height information to predict Dead, okay, this will help. But that was not the case, because when I plotted let me close this. So when I plotted a correlation chart for height, okay, for height with respect to Dead, okay, or let's say this value, okay, so this was not at all significant, okay. So it might be happening was the maybe there is some other feature which is like taking height, okay, and then some product of that was correlating with Dead, but height was not at all like directly correlating with Dead, okay. So yeah, cool. And other features were like yeah, target name, which was the labels, and yeah, the values of them. Cool. So these were the metadata feature. So first thing I had to do, okay, was how to split the data. So that was my first question: how to split the data, okay. So if your data set was not splitted like in a good fashion, okay, it might happen like in your train set, all of your values are like all of your, let's say all of your values for Clover or Dead, okay, are within 0 to, let's say, 1 or something, okay. Because if you randomly split with respect to green, GDM or total, you would get a good split, okay. But if you are not considering Clover and Dead, okay, then it may happen your train set contain values for Clover and Dead in this range, and your val will contain uh, like values, let's say between, let's say, 10 to 20 or something, okay. And this would have like decrease your model performance, okay, because your model will not know like there is like a 10 plus value exists for Clover, okay. And this also prevent the model from like considering these kind of leaves as Clover leaves, okay. Cool. I'll just show you some images. I guess I should have it in, or maybe outputs. maybe Inference. Let's see. Can I increase it? Oh yeah, these are the clover leaves you can see. Okay, so if I zoom it, so here you can see these are the leaves that I was talking about. Okay, these are clover leaves, and here you can see the clover has a very significant amount here, which is 35.1643. Okay, whereas the greeniness is 7, which is pretty low. Okay, but if you consider like everything is green. Okay, so if your split of the data is not nice, or let's say it's not properly done, then what would happen is your model would consider these leafy vegetation as green only. Okay, it will never learn how these kind of shapes are contributing to clover. So yeah, the splitting of data was pretty necessary. So for me, what I found out was, so like in the competition, in one of the famous discussion, it was mentioned that if you split your data with respect to sampling date, okay, along with state, okay, so it was giving a good split. Okay, so what I did was, so I fine tuned it with a ratio of total uh, upon greeniness. Okay, now I did a multiple of iteration. Okay, and after that I was able to see some good splits. Okay, so by doing that I got a good split like this. I'll just scroll down, I guess. Yeah, so here I have basically shown like my 5-fold splits. Why is not going down? Yep. So you can see in my splits, okay, I have a good representation of the whole data with respect to train and val. Okay, so yeah, I don't know why I'm not able to scroll. Yeah, here. So yeah, so across the dataset, like across my folds, okay, my mean and variance was not varying too much. Okay, so I got a good split across all the folds. Okay, so yeah, I just tried different approaches for the split, and once I found it, so I move on to my training strategy. Okay, so yep, cool. So this is how I split my data. Now for the training strategy. Okay, so model you can consider basically. Okay, so for modeling, so I went on to their models directory. So here I observed that Dino v2 was performing really good. Okay, and Google seglib was also working really good. But what I did was, so I, instead of using Dino v2, okay, I used Dino v3. Okay, so in this competition they have claimed that we can use Dino v3. So I use Dino v3 because Dino v3 has a very so it is like working better than Dino v2, and in their paper also they have claimed that they are better than Dino v2. And in terms of like this kind of biomass estimation, so current research community are kind of moving from Dino v2 to Dino v3. So I thought it's a good attempt, like if I use Dino v3, and I can get good results with this model. So yeah, so my foundational model was this, or you can say my baseline model. So it's not that I haven't tried Dino v2, okay, and this VLM model, this siglib model from Google, but Dino v3 was standing out better than these two. Okay, so this was my baseline. So what it gives is like it's a vision transformer model only. Okay, so what it takes is it takes the biomass image. Okay, and it gives me a you can say a feature matrix. Okay, where it divides the image into multiple of tokens. So I will not go to the theoretical part, so you can watch any video, or you can, there are multiple articles like how Dino v3 works. Okay, so it basically gives me a feature matrix in which the first layer is the CLS token, which basically contains the overall representation of the image. Okay, so I took this part. Okay, and what I did was, see, Dino v3 is trained on a vast majority of the data. Okay, it's not specifically trained for this kind of crop images. Okay, it is trained on like your cosmetic images, your crop images. Okay, general images. Okay, because it's a foundational model. Okay, so in order to like apply proper weightage over these features, okay, what I used is, so I won't say it's a exactly a Mamba implementation, okay, but I use a gated feature selective layer over this uh, feature dimensions. Okay, so that layer I was calling it as local Mamba. Okay, so from this feature vector, okay, it was going to my local Mamba where these feature dimensions were getting weighted, okay, using a 1D convolution. Okay, so if you go to my repository, okay, here I have like curated everything that I did in this competition, so you can uh, take this. Okay, so yeah, let's open this. So yeah, I was using this Mamba blocks. Okay, so it's basically weighing how much projection should be should be weighted. Okay, you can say it's a selective feature gating kind of layer. Okay, now once I know what all dimension I have to look, then I was passing it to multiple regression heads. Okay, so since this competition demands like you have to predict 5 labels. Okay, so I was generating 5 layers. Okay, or you can say 5 regression heads. Okay, I think it's better for me to show you the code also. So this is my final submission code. Okay, so if I go to model code, okay, so this was my local Mamba block. Okay, so what it does is basically takes the feature dimension. Okay, it normalizes them. Okay, then it basically performs a sigmoid of them. Okay, now that sigmoid of that gets multiplied with the actual feature vector. Okay, and from that it basically learns, okay, how much each dimension in the feature, okay, should be weighted. Okay, so sigmoid is not the learnable parameter. This gate feature, okay, which is here a linear layer. Here the weights, so here the neurons are learning how much the dimension should be weighted. Okay, so from that um, I was transposing them. So yeah, so to get into a more detail, so what is happening is, so I'm getting a batch. Okay, uh, token. Okay, and the dimension of that. Okay, so when I said I am getting this feature matrix, so per token, okay, I'm getting a d dimension vector. Okay, so this is d. Okay, so I have to apply this 1D convolution over this d dimension vector. Okay, so this is for that. Okay, so you can see like I'm doing a transpose. Okay, then I have this convolution 1D layer where the kernels are applied over the d dimension vector. Okay, and after that I'm transposing it back to the original shape, which is tokens and dimension. Okay, then I have a projection layer, which is again a linear dimension. It also learns so see, you have this feature embedding. Okay, you have to project into a learnable space. Okay, so I have 2 learnable space in the Mamba layer, which is like how much weight is to be done. Okay, and another is from the raw feature itself how much weight you have to done. Okay, so one weights in the sigmoid manner, another just directly weights them. Okay, then yeah, after that I'm applying this dropout layer. Okay, it's pretty standard DL stuff. Okay, then I'm adding the weightage plus whatever I have got. So this is like a residual connection only. Okay, so the shortcut plus x, shortcut is basically the original feature dimension that I have gotten from the model. Okay, so yeah, this is my Mamba layer. Okay, now if I go down, this is not the final model I have chosen, I guess. Yeah, this. Okay, so yeah, So if I show you here, so I missed a step. Okay, so what was happening was, so the image shape, okay, that was given in the competition, okay, so those were around 1024 cross 20248. Okay, so basically 1024 upon 2048 image. Okay, so I'm just denoting them in the OpenCV manner, like height and width. Okay, so what I did was I splitted the image into halves. Okay, because Dino V2 is not trained on this scale image. Okay, it is trained with a so it is trained with a dimension of close to like uh, you can, so it is trained on a high spec image, but the in order to apply tokenization and all that stuff, okay, so your patch dimension, okay, that should be divisible with the image shape. Okay, so for me I have chosen 532. Okay, so what I was doing was, so from the image, okay, I was dividing into two halves. Okay, now this is like 1024 and this is 1024. Okay, 1024. Okay, so this is my left half. Okay, and this is my right half. Okay, now these were getting resized into 532 by 532. Okay, now for each of this portion I was moving it to the vision transformer and collecting this feature matrix. Okay, then after that I'm concatenating them, both the features. Okay, why I was doing what? So see, this is a big image, right? If I simply convert this 1024 by 2048 into a 532 by 532 image, then it may happen like so much of information loss might happen. Okay, because I will be like losing out pixel values, right? Because it will be like what, shrinking the image. But if I convert this into two halves, okay, then I am losing pixel information less. Okay, so that was the major region. But one important note to also produce is, so here not just I have divided into two halves, I have also experimented in dividing this whole image into 8 halves. Okay, uh, so the key idea was like if you divide it into a horizontally also, so this will become like what, 512. Okay, and if you divide it like 4 times, okay, so your 2048 total will get divided into 4 512 values. Okay, I have tried this also, but uh, training this model was little slower. Okay, so this was giving a better performance, but uh, I was compromising with the inference speed. Okay, so in order to tackle that, I have chosen with like 2 split image strategy. Okay, instead of going with 8 splits. Okay, so yeah, so yeah, after I have converted them into left and right halves, I was collecting their feature matrices, I was feature vectors, I was concatenating them via this. Okay, then I was passing it to the Mamba layers. Okay, then once I have them, okay, then I was creating my regression heads. Okay, so as I told you in the competition, okay, the major problem here was how to correctly predict Dead and Clover. Okay, because these images are not majorly found in the dataset. Okay, and for Dead, those were hidden, right? So in order to tackle that, I have done some strategies. Okay, so my first strategy was, so in my EDA, okay, uh, to, 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 okay, so when I plotted the correlation chart, okay, so basically I wanted a feature that can highly correlate with Dead. Okay, at least Dead or Clover. So what I found was, so the ratio between my Dead and so the ratio of Dead with respect to total uh, biomass, okay, that has a very high correlation with respect to Dead. Okay, if I show you here this 0.84 and this. Okay, So my strategy was, I will train the model, okay, to predict the ratio, okay. So my idea was, so I have a regression head that is giving me the value, okay. Then also I will predict the ratio of it, okay. That ratio, when I am like when the model is estimating, okay, or less, when it is predicting, I will multiply that with the total biomass prediction, okay, and that will also give me a dead value, okay. Then I can then average them out. So that was my idea. So you can see, like, ratio head I have done for dry, for dead and clover, okay. Then also what I was doing was, um this deriving of this dead and clover, okay, I was doing a EMA value also, okay. This is for that, okay. So this is like all from experimentation and all that, okay. Here you can see, like, as I'm getting the image, I'm dividing into left and right half, okay. Then I'm concatenating their feature vectors. Then I'm passing it to the fusion layer. Fusion layer is basically my Mamba layer, okay. So there is a sequence of Mamba layers, okay. Then after I got that, I'm performing a pooling, okay. Then I was passing it to all my regression heads, okay. Now if you observe my dead and clovers, okay. So first I was calculating, like, predicting the dead and clover ratio, okay. Then I was predicting, like, from the predicted values from my regression head, okay. So as I have told you here, okay, here, okay. So total is basically a summation of my GDM and dead, okay. So since I was lacking in dead and clover, okay, so I can use this relationship to satisfy the prediction, or like to make better prediction. So what I was doing was, so my predicted GDM and total, okay, I was subtracting them to get a dead value, okay. Why I was doing was, so because in the competition these values are high, so my model was able to predict them correctly, okay, as compared to dead and clover, okay. So I had higher confidence for predicting green, GDM and total, okay. So if I'm predicting them correctly, then the subtraction value of them, okay, that should be close to the actual dead value, okay. So that was the major inspiration, you can think, okay. So yeah, you can see, like, from the core, so that's why I'm written from the core, okay. Core meaning like the major confident values, okay. So yeah, I was subtracting them for total minus GDM, that was giving me dead, okay. I was performing a ReLU so that my values won't be negative, okay. Similarly I was doing for clover. So clover is basically summation of difference of my GDM and green, okay. Since I was doing good in this two predictions, so I was taking a subtraction of that to get the clover, okay. Then yeah, this is for my core. Then since I was predicting the ratio also, okay, so from the dead ratio that I have predicted, I was multiplying them in the total, okay, to get the dead amount using the ratio, okay. Then I was taking a average of the dead value that I got from the difference and the dead value that I got from the ratio, okay, to get that, okay. And yeah, this was one more thing that I did. So I just wanted the model to learn how to predict dead and clover, okay. So for that I have created this two parameter vectors, okay, to predict dead and clover also, okay, instead of doing this regression head, okay. So I was hoping my model will learn, okay. So but it didn't actually, okay. But yeah, what I did was, so from that parameter value also I was predicting my dead and clover, okay. Then I was doing a EMA of that, okay. So EMA of the model learned dead value plus 1 minus of this mixed dead, sorry, I think I lost here, okay. So this is the derived value that I got from the ratio and the core, okay. Then I have this mix dead, okay. So this was basically like how much to trust this derived value versus how much to trust this dead value from the regression head, okay. So this was for that, okay. So yeah, this parameter that I have, that is the learning parameter, like the learning parameter for the model, it was basically learning how much confidence should it give to the derived value versus from the regression head. Okay, so yeah, this was for that. Now from this I will get new dead and clover values. Okay, but in order to satisfy this constraint, okay, which is like my GDM should be green plus clover, my total should be GDM plus dead. Okay, I was replacing the predicted GDM and total value with whatever dead and clover value I got. So I was again computing the GDM, okay, and I was again computing the total from the summation constraint. Okay, so here I was not using the regression heads values. Okay, because these values will satisfy my biomass physics constraint. Okay, but if I directly use them, it may happen whatever value I got from here, those may not satisfy the physics constraint. So yeah, after that I was giving out the total 5 values, okay, from my neural network. Cool. So this is what is happening here. So you can see this mermaid flow, which is basically telling you the whole story that I did during training, or like this is the whole architecture of the model. Cool. And yeah, this was giving my predictions value. Cool. Now my model was giving out values. Okay, now for me to choose a loss function, okay, I was doing I was doing a combination of two loss function. Okay, since my model was learning two things. Okay, uh, my model was learning from the regression head. Okay, the direct value, you can say, and from the ratio head, okay, percentage of that. Okay, so I was using a mixture of two loss function. One is my friendly cross entropy loss function. Okay, and the other loss function that I use is the Hubbard loss function. Okay, okay, so I was using Hubbard loss over the ratios uh, because I cannot apply my okay, I think I have misread this. Okay, so this was not MSC. Oh, sorry, this was not cross entropy. So this was a MSC loss function. Okay, for the regression heads. For the ratio heads, I was using Hubbard loss. Okay, so for the regression head, since I was predicting directly the values, MSC was a good loss function for them. Okay, but since I need to but for the ratios, okay, I was using Hubbard loss because ratio should be within 0 to 1, right? If my values goes beyond 1, okay, I should penalize my model more. Okay, but if my value is within 0 to 1, okay, but it is making mistakes around the ratio, then my loss function shouldn't penalize with a L2 norm. Okay, because in L2 norm what we do is we do pred minus ground truth whole square, right? So if my values are between 0 to 1, this whole square will give me a very small value. Okay, so here instead of squaring the loss or the squaring the error, I should simply remove this square. Okay, and I should only trust a MAE kind of structure. Okay, where my pred minus GT should give me the error. Okay, so basically it's a L1 norm here. Okay, so this is what I was doing in Hubbard loss. So this is what Hubbard loss does. Okay, when your error is after a certain value, okay, it basically uses MSE. Okay, otherwise it converts the error directly into a MAE error. Okay, so that was the inspiration why I used Hubbard loss for the ratios. Okay, so I guess I have mentioned it here also. So if I open the training strategy, so this is my whole training flow. Okay, So yeah, here you can see like for RMSE I was using the weighted RMSE, okay, so that it will penalize more on total biomass prediction and GDM prediction, okay, and for ratios it will use Hubble loss, okay. Then yeah, after all that constraint, so I was like what updating, like performing back propagation and all that stuff, like standard DL stuff, and yeah, I trained the model for every 50 pox and with some model checkpointing callbacks also, so that I will save the best model, okay. So this whole flow translates like whatever things I have mentioned till now. So yeah, you can also see like what all augmentation I did. So I did some resize, some vertical and horizontal flip, okay. So some random shadowing, because in the images if I show you, okay, there were some shadows of the camera, okay, over them, which were like taking the pictures. So you can see like there is a shadow here, okay. So I was putting some random shadows so that my model will get accustomed to like there are some shadows present in the image. So with respect to that I have to get give correct value. So here also you can see like there are some shadows. So yeah, the model was learning all that. Cool. And other augmentation will be some Gaussian blurring. So there were some cases where some images were blurred out, so I just applied some Gaussian blurring, and yeah, then there is normalized. It's not exactly a all augmentation, but yeah, it's basically like when you are giving to the model, I was normalizing the value, no, like normalizing the pixel value. Cool. So yeah, this was the overall flow of my training. Now, with that, um, when I was submitting to public leaderboard, okay, it was only giving me a 0.69 score, okay. So I was not improving on that, okay. So I have tried like many other techniques with the models, okay, like model building, some data set splitting also I tried, some more augmentation I applied, but I was not improving above 0.9 score, okay. So what I did then is I thought like since Dino V3 is capturing good quality of features, why not try some classical models, okay. So then I move on to some classical approach, okay. So because yeah, this notebook contains it, okay. So what I did was I collected all the Dino V3 embeddings, okay, for my images, okay. Then I went on to training some classical models, okay. Now the thing was my uh, yeah, so the model gives a 768 dimension feature, okay. So if you use any tree model, okay, or yeah, any tree based model, so those will basically underfit, okay, because there are so many features, okay, to learn and use to like split the data, okay. So the major task for me here was to reduce this feature dimension shape, okay. For that I used PCA, okay, to analyze which dimension was performing well across all the models, okay. So this notebook contains like that strategy, okay. You can see like selecting the best parameter for feature like PCA, okay. So I did multiple iterations, okay. So where I was like fitting like light GBM, XZBoost, linear regression, lasso, elastic net, linear regressions, SVC, random forest, all the regression type models, okay. And this was my PCA grid. So basically I was converting that 768 into one of this feature dimension, okay, and then I was fitting all the models, okay. So from that I was getting this yeah, getting this final report, okay, where I observed that majority of the models are giving better score when the feature dimension is 64, okay. So basically convert those 768 features into a 64 dimension feature vector and then use your classical models, okay. So yeah, now from this PCA report, okay, I selected the top 3 models, okay. I thought like using this XZBoost and yeah, you can see like only one gradient boosting tree model is there, okay, only XZBoost is there, okay. Light GBM and random forest and not at all there. Okay, so yeah, I went on to pretty linear approach. Okay, so I took the top three models, which is like Ridge, Lasso, Elastic Net. One mistake I did was during inference, I didn't went to Elastic Net. Okay, somehow I flipped the switch to linear regression. Okay, I took the top fourth model for fitting. Okay, but like I can argue also like the performance was not like those performance were pretty much similar between elastic and linear. Okay, so yeah, in my final inference pipeline, okay, if I show you, so I was basically using yeah, linear regression, elastic net, and ridge regression. Okay, so I was, where is that tab? Oh yeah, I didn't use lasso. Shit. Okay, I didn't use lasso. Yeah, maybe that's the reason why I landed up in 149. Maybe that's the reason, but yeah, I could have done better if I used the top three models. But yeah, so from this I chose the top three models. Okay, and I set the PC parameter to be 64, and then I trained them again, and I saw the results. Okay, from this what I observed that these classical models are giving me the prediction in a negative dimension also. Okay, so you can see for green, okay, clover, okay, couple of dimension, like couple of predictions are negative. Okay, which shouldn't be happening, right? Because biomass is a you can say it's a real number which is should always be more than 0. Okay, or like more than equal to 0. Okay, but since they were giving negative values, so I had to do something to like circumvent this, right? Because if these are negatives, then other predictions will be bad, right? So yeah, so this is where I employed a mass balancing strategy. Okay, so this was the it doesn't look this, yeah, so this was the classical model training flow. Okay, where for every image I was running Dino v3, I was collecting their CLS token. Okay, and from that vector I was training this ridge, elastic, and linear model. Okay, then I was ensembling them. Okay, now during ensembling, the model predictions were becoming negative, so in order to prevent that, I was clipping out the values. Now when I am clipping out the values, it may happen they may not satisfy these constraints. Okay, which is like GDM should be green plus clover, total should be GDM plus dead. Okay, so in order to satisfy this physics constraint, okay, so I went on to some public notebooks. So those people were also having some issues. So one of the voted notebook had a strategy of using Lagrangian multipliers. Okay, so uh, and that was the main idea behind this yeah, mass balancing projection. Okay, so the idea was pretty simple. Okay, so basically I had some constraints, right? So I know my green plus clover, okay, should be equal to my GDM prediction. Okay, so I can have a constraint like minus the GDM quantity should be 0, right? Because the summation of this two will result in GDM. Okay, so this is constraint 1. Okay, then the second constraint is my dead plus GDM, okay, they should be equal to the total biomass present. Okay, so I can subtract a total. Okay, and this should be 0. Okay, so these are the constraints. Okay, so my predicted value, okay, let's say that is X. Okay, where X is basically all the predictions, and where it is predicting let's say green, clover, dead, GDM, and total. Okay, let's say this is the prediction matrix. Okay, so I can apply this constraint something like this. Let's say my constraint matrix is A. Okay. So the vector, so the matrix multiplication of this should give me a 0 value. Okay. So where my A is, so with respect to first constraint, it will be 1, 1, 0 for dead, GDM minus 1, and total should be 0. Okay. So if I multiply this with this, okay, this will result into this equation. Okay. Similarly for the second equation, okay, here I will say constraints. Okay. So for the second equation, I can write it in a matrix format where if these are my fields, I can set green as 0, clover as 0, dead as 1, GDM as 1, and total as minus 1. Okay. So when I multiply this value with this, I will get back this equation. Okay. So yeah, so my constraint equation when done matrix multiplication with x should equate to 0. Okay. Now if my constraint is not giving me x, like so if using this constraint matrix and the prediction that I've got from the classical models, okay, if that is not equating to 0, then I need to correct this x. Okay. Now this is a error minimization problem where let's say x prime is the corrected matrix, okay, which when multiplied with this A will give me 0. Okay. So I should project my predictions, okay, in such a manner so that the actual corrected values, okay, minus whatever prediction I did, okay, their distances should be small. Okay. So here x prime is the actual corrected matrix, okay, of my preds, okay, where x is my prediction. Okay. If I can find this x dash, okay, such that x dash minus my x should be minimum, okay, then yeah, such that a x dash should be 0, okay, then I can project my prediction into such a space such that I will satisfy my biomass constraints. Okay. Okay. Cool. So you can think of like this is kind of your f of x. Okay. So if you guys have heard about Lagrangian multipliers where you have a convex function, then you have to give out the maximum or minimum respecting another constraint function. Okay. So in that kind of case, Lagrangian multipliers help. Okay. Where you project to divergent from your f of x and from your constraint x, and you try to find the best multiplier for your constraint vector, constraint divergent. So that's the idea here. Okay. So basically this becomes my f of x and this becomes my g of x. Okay. So I need to minimize this f of x such that it will satisfy this condition. Okay. So if I write it in the form of Lagrangian, okay, so it will be something like x prime minus lambda, okay, lambda equal to this is my f of x, okay, I can say minus lambda of g of x. Okay. So I can use a plus or minus sign because lambda is a free variable here. Okay. So I need to find this lambda. Okay. So it can take like plus or minus. So I'll write it like this. Okay. Because it's easier to learn. So yeah, f of x and this. So if I write it now, so my Lagrangian equation will become minimize x prime minus x, the L2 norm of them, okay, plus lambda times a x prime. Okay. So when I'm writing into this Lagrangian form, that means when I take the divergent, okay, of Lagrangian with respect to x, okay, that should equate to 0. Okay, that basically means when I'm writing these two equations, okay, that basically means they are satisfying Lagrangian. Okay, now if they are satisfying Lagrangian, then this whole equation should be equal to 0. Okay, so if I do the differentiation here, okay, so this divergent is basically what now one thing to remember is, so all these are matrices, these are not your scalar values, okay, but this is a scalar function. Okay, so when I'm taking this divergent with respect to x dou of dou x, okay, this is a scalar. That means if I write it here, minimum of x prime minus x L2 norm plus lambda a of x prime, okay, that should be 0. Okay, so here when I'm doing the differentiation, I should be doing matrix differentiation instead of scalar differentiations. Okay, so now I can write this form as dou of dou yeah, it should be x prime. Okay, x prime, so this will be x prime minus x transpose x prime minus x. Okay, so I can write the L2 norm like this. Okay, plus lambda dou of dou x prime a of x prime equal to 0. Okay, cool. So if I differentiate this, okay, this will basically turned out to be this is lambda, this is a, okay, and this will give me matrix. So if I take the differentiation, so this should come out to be, I think I'm missing a transpose here. Okay, so that's how it should be defined. Okay, because this guy should give me a scalar. Okay, so I should multiply lambda. Okay, and this should be transpose, so here it should be transpose. Okay, okay, and this should result in a differentiation where I'm getting lambda a transpose. Okay, if I take the differentiation, okay, that is equal to 0. Now when I'm taking a differentiation of this, this will turn out to be 2 times x prime minus x. Okay, cool. Now what I will do is I will write x prime with respect to my x, so I will try to find my x prime here. Okay, so x prime will become x plus minus half of lambda times a transpose. Okay, so this all I'm doing just to explain you like how this biomass is getting applied. Okay, how I'm getting this corrected matrix value. Okay, this is using this Lagrangian multipliers. Okay, so yeah, now I got x prime here. Okay, now if I write my constraint equation, okay, so my constraint equation should satisfy now. Okay, so if I write my constraint equation is saying x a times my x prime, which is the corrected actual predicted value, that should be equal to 0. It implies that a times my x minus half of lambda a transpose, it should be equal to 0. Okay, now I can find my lambda. Okay, so this will be a times x minus half of lambda times a transpose a, this is equal to 0. Okay, now if I write my lambda in terms of this, so my lambda will become, so 2 times ax. Okay, now this 2 I can write inversely also, so or I can say like 2 times ax, and this will go as a inverse of this. Okay, so a transpose a inverse, so this will become my lambda. Okay, so basically you are in matrix space, so this 2 will get multiplied here. Okay, and this 2 will be dividing here, which is essentially saying it you have to take inverse of them. Okay, so my lambda becomes this. Okay, now I know my x prime is x minus half of lambda times a transpose. Okay, so that I can simply say as if I plug in the lambda value, so my corrected model prediction will become x minus, which is the model prediction, minus half of my lambda value. My lambda is 2 times a x a transpose a inverse upon with a transpose, which is this a transpose here. Okay, now 2 are scalar, so this will get cancelled out. So finally my corrected model prediction will become x minus a x a transpose a inverse times a. So yeah, I know x which is basically my model prediction. Okay, and I know this a, which is the constraints. Okay, so using this prediction and constraint, I can correct my model prediction so that they will satisfy the biomass equations. So yeah, I use this and I can show you this. Where did I apply? I'll just search for it. Let's say mass balance. Yeah. Yeah, so here is how I did it. Okay, so this is my constraint space. Okay, then I found the matrix inverse. Okay, and which is this a, here you can see the equation here. Okay, which is a times a transpose. Okay, then I was just like calculating some residual, but b is here essentially 0. Okay, so it may happen like for this case my constraint was a times x prime was 0. Okay, you can also use the same equation when your let's say a times x transpose is something other matrix. Okay, some c or something. Okay, so the equation will stay something like this. It will just add up your C matrix here. Okay, but yeah, here C matrix was a 0 matrix, so I don't care for it. Okay, this is just, I have written this B. Okay, for the constraint term. Okay, and yeah, here after that I was performing the correction, like subtracting the correction value. Okay, with my model prediction. Okay, then also just for a safe case I was doing zero correction. Okay, so if let's say even after constraint, okay, this mass balancing, I was getting some zero values. Okay, like some negative values, just convert them into 0. Okay, so yeah, enforce mass balancing. So this is what happening with the classical model. So this was the mass balancing idea, where using the Lagrangian equation I was correctifying my model prediction. Okay, and after that I was predicting 5 values. Okay, and this was giving me another summation. Okay, so with the classical models I was able to get somewhere around like 0.65. Okay, with all this assembly. So now I had like 2 models. One is giving like 0.69. Okay, and other was giving 0.65. So what I did is I did the ensemble of them. Okay, I took the average of them, weighted average. Okay, so you can see in my final summation. Okay, so yeah, so for the neural network model I was giving a weightage of 7.79, and with respect to the classical models, okay, I was giving a weight of 0.66. Okay, oh, I was saying 0.69. I was getting 0.71. Okay, which is good. Okay, cool. So yeah, this was the idea. Okay, so I did the ensembling of them. Okay, my my neural network and the classical models. Okay, so somewhere here I may not be using the leaderboard scores. Oh yeah. I was stating it here. Okay, but what I was actually using is this weight. Okay, so I was weighing my neural network prediction 65, like 65%, where I was weighing the classical model output 2.35%. Okay, so with that I got my final summation, and somehow it resulted in the best performance across all my submission. Okay, so it gave me the highest performance. You can see, like, uh, in the public leaderboard it stand out to 0.71. When it evaluated against the private leaderboard, it was giving 0.61, 865. Okay, and this was the submission I did, and it landed me upon this 149th position, and I got my first silver medal. So yeah, that was the major pipeline and all that I have explained here. Okay, so whatever I have told, okay, I have documented it in GitHub. Okay, you can I will add this link in my video description. You can look into it. Okay, how I was performing all this. Okay, and here also I have mentioned the mass projection equation and what I was doing, and here's the final image of my final submission. Okay, where I have concatenated the Dino v3 neural network pipeline and the Dino v3 classical model pipeline. So yeah, I just took like 14 days for this competition, and some honorable experiments I wanted to try was, instead of using Dino v3 here, I could have switched to some other models. Okay, some people were using siglip model for this pipeline processing. Okay, like for training classical models. I didn't use that. I thought I didn't have time actually. Okay, I could have experimented, but yeah, somehow this experiment gave me my first silver medal. I'm happy. Okay, 14 days of work, so that gave me this. Cool. So that was all for this video. Okay, I can show you some model predictions. Okay, so this is how the model prediction looks. Okay, so if you look at it, so yeah, you can see, like, I think the model prediction are not that great here. Okay, so green, the actual ground truth value is 0.45. Okay, where my model is predicting 8. Okay, and yeah, for Clover, okay, somehow my model is pretty close to that. Okay, and error of 0.9. Let's look at some other images. Okay, so here I guess there were pretty much dead particles here. There are many straws I can see. Okay, so dead should be high, and yeah, dead is very high. Okay, my model is 2.9 margin error. Okay, and yeah, here I can see some clovers and greeniness, so it should be a mixture of that. So yeah, greeniness 40, my model is saying 19. Okay, that's not good. Okay, clover is 5, my model is predicting 8. Okay, plus 2 margin. Okay, so yeah, so this is how my model is predicting. So yeah, that's all for this video. So if you like this video, and if you like the pipeline and my explanation, please do subscribe to the channel and give a like to this video. Okay, and yeah, if you find any part difficult to understand, and if you want to know why I did it, and just ping me in the video section, so in the comment section, so I will be happy to answer you. Okay, and since you know, like, the overall process what I did. Okay, and if you want to try out my repositories, so because all the code bases are here. Okay, you can easily download this dataset. Okay, because right now it is in public mode. Okay, so you can download this dataset, and you can clone my repository. I have also added all the packages that I have used. Okay, you can run it in your local, or you can run it in a collab notebook, so all that thing you can do. Okay, maybe you can build another model which beats my public leaderboard score or my private leaderboard score, so just do it. Okay, and if you were able to beat my scores, then yeah, you can ping me in the chat like I beat your score. So I'll be little sad, but yeah, I'll be happy, like I was helping you guys to improve. So yeah, and also beat me. That's not a good thing to do, but yeah, you guys can try. Cool. So that was all for this video. Happy, I hope you enjoy this video. So yeah, just stay tuned to watch more videos. I'll be posting more videos on Kaggle competition, and how I'm participating, and what are strategies I'm doing during inferences, and how to submit and all that stuff. So yeah, just stay tuned to watch more on this. Cool. Bye bye.